first of all, as usual, a check for the virtual classroom. Those who are connected, can you hear me? Yes, somebody's answering, so, okay. Okay. Okay, let's wait for the people to sit. Okay, so let's start from where we left. Last time we introduced linear discriminant analysis as both a way to reduce dimensionality and to perform classification. The idea was to look for a direction over which the classes can be well separated. In which sense? In the sense that if we have two classes and we want to perform binary classification, what we can do is to look for a direction over which we project our samples in such a way that then we can use a simple rule. Whatever is on one gets projected above a threshold will be labeled as class 1, and the rest will be labeled as class 2. So we're seeing LDA as a way to find a good direction for the projection. The idea here is we want to have a direction over which the class means are far compared to how scattered, how distant are the points of each class from the corresponding class mean. So the ratio is large if the classes are far and the points inside each class are close to the corresponding mean. That is probably, we see last time, a good direction for classification. Then we have seen that we can extend the method to perform dimensionality reduction by looking for, rather than one direction, for multiple directions. In this case, we need to define a criteria that defines which directions we will pick. And we said we can generalize the binary version of the problem, the two-class problem, to n class problem, and from one direction to m directions, by taking the generalized, the right eigenvectors of SW-1 SB. This allows us to obtain a set of directions over which we project our data. In contrast with PCA, here we didn't require these directions to be orthogonal. We didn't ask for the directions to be orthogonal, so in general the projection may not correspond to orthogonal coordinates of projected points. What does it mean? It means that if I have an original space, LDA may find directions which are not orthogonal. So my coordinates would be the projection over the two vectors. These are not orthogonal coordinates anymore. If we need, we said we can always transform our matrix W into a matrix that represents, whose columns represents a basis for the same space identified by LDA. This is not the LDA solution anymore, but if we are interested in projecting the data into the space which contains the most discriminant directions, that's typically enough. And as we will see later, the difference is that essentially there is a difference, linear transformation between the two representations that typically is irrelevant for whatever comes next, with few exceptions. So typically we will not distinguish the two cases. And in any case, we when we use LDA, typically we use it before some classifier, and as we said last time, typically either our classifiers are invariant to linear transformations, or we will need to deal with the fact that they are not invariant in any case when we discuss the classifier itself. So from the point of view of LDA, for the moment, for us, those are both possible definitions. Either we look for the W that corresponds to the solution of LDA, or if we need and we want to project into a subspace, so orthogonal directions, we can look for the W and then orthogonalize the columns to find a basis for the corresponding space. The results are different. They may be useful in different contexts. As I said, if needed, we will make the distinction when it's relevant. For the moment, we just stick with the solution provided by the standard LDA. We have said we can identify at most C minus 1 directions because of the definition of the between class covariance matrix, which has only at most C minus 1 non-zero eigenvalues. So we can identify only C minus 1 directions for which the corresponding eigenvalue is non-zero. All the other directions would correspond, from the point of view of the LDA criteria, to directions where there is no separation between the classes. So these are irrelevant directions. You can find as many as you want, up to the size of the original space, of course, but from the point of the LDA, those are all irrelevant directions. So if you try to solve the eigenvector problem and take all the solutions that you find, the first C minus 1 will be good. All the rest, whatever you take, is like picking random directions in the remaining space. So picking random directions that do not really have no reason to be picked instead of others. So which one you pick will be essentially like selecting randomly the directions, which doesn't make much sense. If you want to pick random directions, just use random function and create random directions. Now, here you can see how the three models would find, the three approaches that we discussed would project the data over the first direction. For PCA, first direction, here we have the line that connects the two class means, which corresponds to the eigenvector of SB for a binary problem. And LDA, I said first direction, but for LDA it's the only one, because for a binary problem, C number of classes is 2. So the maximum number of LDA direction is 1. You can see with PCA, for this data set, projected the data in a way that shows loss of overlap. It's difficult to find a threshold that does not introduce loss of classification errors. Remember that our classification rule with LDA is we project over a direction, and then whatever is larger than a threshold is assigned to red, and whatever is lower will be assigned to blue. Here you can see that if I put the threshold here, all these blue points will be misclassified. A bit better with the line that connects the class mean, but still not very different from PCA. With LDA, you can see that here I have a direction. If I put a threshold here, the amount of mistakes that I make is quite limited with respect to the other solutions. So indeed, I found a direction that is more discriminant. That is a direction over which the two classes look farther away, they have less overlap. Now this I said we see during the maybe laboratory. Now, one thing that we didn't say, but let's first look at, well, we need to say what we are showing, is that up to now we assume that the within class covariance is non-singular. That is, that that we can invert SW. This is typical, this may not be always the case. Why? Again, consider the MNIST, the digit recognition problem. You have your pixels, you have your images, and now take the top left corner of each image. what do you expect that corner to be? Typically, it will be all white for all patterns, which means that if we represent these as arrays, regardless of the class, here I will always have 1. Within class variance over this direction is 0. Also between class variance over this direction is 0. There is no variability over that component of the vector. So if you were to plot, if this was the first pixel, it's like all the points are aligned at a single value of white for that pixel, for all the classes. How can we address this? Well, usually when we have low within class variance, we also have low between class variability. If not, then that's a discriminant direction, but we should ask ourselves whether, well, if not, typically that's a good direction, but the way we will see with LDA, we may have trouble identifying that specific direction due to numerical errors, but we will discuss that in a moment. But typically, like in this case, we have low within class variability because there is low variability in the dataset along that direction. How can we solve the problem? Well, is that pixel relevant to distinguish between classes? If all the images have a top left corner that is white, is that information relevant to distinguish the different classes? No, because if I tell you the top left pixel is white, that doesn't give you any information on which is the image that is inside the number that is inside the image, because all the images have a top left corner that is white. We have seen that we can remove directions that have low amount of information by using PCA, where low amount of information means what? Low variability. We've seen the directions that have low variability can be removed by a method that reduces dimensionality, because low variability means that if we remove those directions, we will make a low error. The error that we make by removing directions with low variance is limited if we measure the error by Euclidean distance. It makes sense. If I strip this direction, I know I can perfectly reconstruct my images because I know that the top left pixel will be white. So even if I don't represent my top left pixel in my vectors, so I reduce the dimensions and I remove this component from my vectors, I didn't throw away any information because I know that all the images in that component had previously a value of 1. But PCA does exactly this job. When the variance along the direction is small, PCA will remove that direction. So for this reason, one way to address this problem is to apply PCA before we apply LDA. If you apply PCA, PCA will throw away directions with low variance and will give you directions that are linear combinations of the other pixels. But the important thing here is that it will throw away components that have low variance, and that means that it will allow us to work in a lower dimensional space where the within class variance will again be well defined, because if we remove directions with low variance, we are definitely removing the direction with low within class variance. Remember that the within class variance, we have the rule that the covariance matrix is equal to between plus within. If we remove direction with low variance, we are also removing directions with low within class variance. If a direction has a large within class variance, then the variance of the dataset along that direction is also large. Makes sense. If my classes are spread with respect to the class mean, even if the class means were perfectly the same, the variance over that direction would be large because there will be lots of spread among all the points. So PCA, if we apply PCA and remove directions with low variance, we are sure that when we apply LDA afterwards, we will not have a singular SW anymore. It remains to see what happens when SB is large and SW is small, but then probably that is an interesting direction to keep, because it means that there is no variance between the images, and all the images look exactly the same, but exactly the same inside each class. So for example, all pictures of the seaside are exactly blue. All pictures of the countryside are exactly green. Now, this is not true in general, but you can imagine that the variability of the color of pictures of green is maybe small. The variability inside the pictures of blue is small. You can imagine that if this is very small, but the classes have very different values, then that's an interesting direction to keep. Actually, in that case, the problem is that our eigenvalue problem, we cannot solve it directly, but because the eigenvalue would tend to infinite. From the point of view of our objective function, having a large eigenvalue is a good thing. So those directions are directions we may want to keep. Typically, the problem is that in this case, when SB over a direction is large and SW over the same direction is small, the problem is more numerically than really a problem from the point of view of LDA. That's a direction that I want to keep. Probably I cannot directly invert SW to find the solution. One thing that we can do is, rather than using direct SW, we add a small value to the matrix, which will not change for epsilon small enough. This will not change the directions, but will make the model robust when I need to estimate the directions for directions where SB is large and SW is small. Again, this is something that we will not need for our project. And for the laboratory, just a thing to know that there are numerical approaches to also address the case where SW is singular, but SB is not. When both are close to singular, it means that the dataset over the direction has low variance, so probably applying PCA is helpful. Now, one thing that we can say more, and that also gives us some additional information on PCA, is that typically one case when we can have, we have seen one example of the case when the within class variance is zero, is close to zero. The pixel of the top left pixel of the image is the same for all classes. Another typical example is when we have, for example, a two-component feature vector, and the second component is just a scaled or rescaled version of the first one. So, for example, you measure the height of a person, and then you build a feature vector where you have the height in centimeter and the height in meter. Then you pass it to the machine, dropping the unit of measure. All the points will be on a line, because the height of a person, whether represented in centimeter or meter, is just a linear scaling of the other. In this case, we say that the features are correlated. When the features are correlated, what do we observe? We observe that they are aligned in a way similar to this, which means that there is a direction over which there is large variance and a direction over which the variance is almost zero. Again, we need to apply PCA to this kind of problems if we need to invert covariance matrices. In this case, PCA does what? In this case, PCA finds the direction over which, let's say, a direction, a new component, it essentially separates the two feature vectors into two uncorrelated components, the first of which will contain most of the variance of these two components, and the second, no, little variance. In a case where there is perfect correlation, essentially the first direction will contain the information, the real information extracted from the feature, while the other will be a direction where there is essentially no variability inside my dataset. So PCA, in case of correlated features, will also be able to reduce the correlation by throwing away, by essentially identifying for correlated features the direction that really contains the information and separate it from the direction that does not contain actual information. So typically you will find that PCA is also used as a preprocessing where you have correlated features to reduce the amount of correlation inside my dataset by throwing away those components that do not add really information inside my samples. But again, for us, we will not use it in this way. Now, let's apply LDA to MNIST, and for the reason we said before, when we apply LDA to MNIST, we will always apply PCA before, because we know that SW is singular for the MNIST, for the reason that we have said before. This was what you obtain with 9 directions. Why 9? Because here it's wrong. We have 10 classes, so we can have at most 9 directions. So C minus 1, C is 10. So I can have at most 9 directions. LDA versus PCA. What will we observe? Well, we observe that here is slightly less, is much more difficult to recover the original image. Let's look at this one. This one looks like this. It should be this. So we don't see the original image anymore. It's a much more, maybe not completely evident, but it's much more clear in the PCA version of the image. Why? Because PCA tries to reconstruct the image as good as possible. That's not the goal of LDA. LDA is trying to find directions over which we can separate well the classes. What does it mean? It means that it finds directions so that when we project the data, essentially images of the same class will be close and they will be far from images of different classes. If you look at these images, you see that for the same class, what you obtain are images that are much more similar between themselves than what you get with PCA or in the original dataset. And you can clearly see a difference with the images of the other classes. So it's doing exactly the opposite. It's throwing away, for example, for this one, it's throwing away the information that is irrelevant for the classification, and it's trying to normalize all images so that the images of one looks something like this. And in contrast, you can also see that it tries to make them different from images. Okay, this last thing that I'm saying, skip it. So it's trying to make images of one similar. So the different ways that I had to write one will end up in images that, when reconstructed, look similar among themselves, because the projections of these images will look similar. They will not look really like a one, but they will be similar between themselves and different from the other classes. That's exactly the goal of LDA. We don't care about reconstructing well the original image. We care that we find directions over which the classes are clearly distinguishable. So 9 directions we have available. In these 9 directions, we will try to make all zeros look similar while they look different from the other values. And here you can see what happens when I apply our Euclidean distance classifier, that is the threshold classifier we've seen last time. So the classifier we've seen last time, we can see that, sorry, this is not the classifier we've seen last time because we have seen it for binary problem. The Euclidean classifier for multi-class is the classifier where I take my projected sample and I compare it to the mean of each class. We can see that what we obtain here is a much better result. Now, to be fair, we should also say that this is not a fair comparison with PCA, but I will not explain why. Maybe we will say a word when we see this model again in 2 weeks with a different explanation. But in any case, here I followed a different approach. I used LDA as a preprocessing followed by the Euclidean classifier, and I got, with 9 directions, a result that is half that of PCA. And notice that it's even better than what I had with original Euclidean classifier. So I was able to identify directions and I was able to identify transformed points such that the Euclidean classifier, using just those 9 directions, is able to provide me better results than an Euclidean classifier trained over the original features only. Now, last couple of words. All we have seen works well if data can be separated by linear classifier, or if it makes sense, we will say which are the assumptions of LDA once we will formalize LDA to another model. We will show that they are equivalent. So from that model, we will derive the assumptions of LDA. But for the moment, let's say that when linear transformations are good, then these methods will work. But there are cases where linear transformations are not good. Imagine you have a data set like this, 2 classes. Now, whichever direction you project your data on, your histograms will look pretty much like this. And you will never find a good threshold to say on one side it's red, on the other it's blue. Of course, we may devise different approaches, like saying whatever is outside of a range is blue and inside is red. But that's not a linear classifier, and it's not a linear method anymore. So that says what? That sometimes linear models and linear methods are not enough. The way that we will deal with linear methods is essentially through transformation of the data that allow us to apply linear methods to transformed samples. How? Again, let's take this example. In this example, if I apply directly LDA or PCA on this dataset, let's stick with LDA. LDA to classify those data, I will never find a good classifier. However, if I transform my samples and represent them using polar coordinates, on the x-axis I have the radius, and on the y-axis I have the angle in radians. This is how my points will look with the new coordinates. Same information represented in a different way. I didn't change the information. I can go from one representation to the other for any point, so I can always, given one, reconstruct the other. So I didn't change the information, but now it's clear that here I can separate my classes with a plane. With a plane oriented in this way. So this is the separation rule, and this is the direction over which I will project my data. If I project my data over this line, I will have that all the red points will be on this side of a threshold, and all the blue points will be on the other side. So linear method in this transformed space corresponds to what? Corresponds, if I were to draw this in the original space, to a separation that looks like this. Whatever, remember, this is radius. Whatever is inside this sphere below a given radius will be assigned to class red. Whatever is outside, radius larger than t, will be assigned to the blue class. So I can achieve a nonlinear classification rule through a linear model in a space that contains a different representation of my feature vectors. And we will see how to build these transformations. There should be unequal. Okay, questions on this? On LDA in general? Yes?
Higher variance feature classes. Isn't that am I totally wrong?
No, it's not the same as clustering, because in clustering you don't have labels and you just rely on your concept of distance to find groups that look similar. But depending on the way you define similar, you may end up with different quantities. So clustering may say these points are similar. Another clustering algorithm may say these points are the clusters. So the clustering is trying to identify similar points inside my data. LDA is not trying to identify similar points. LDA is trying to find a way to look at my data. Remember that a direction in my data set, that direction over which to project is a way to look at the data. So you look at the data from this point of view. It's trying to find a way to look at the data so that the points of the classes that already exist and are defined will be well separated. Which again doesn't mean that the points are similar. For example, let's draw it like this. Classes like this. If this was a clustering algorithm, it would look like a set of points like this, and probably your clustering algorithm would start doing things like this. So it tries to find blobs of things that are similar. Here I'm not trying to find blobs. I already know what is similar and what is different. I'm trying to find a way to highlight what is different and what is similar. So to find a way to look at the data, so I look from this direction, and from this direction I see that the red points are in some region, the blue points are in a different region, and the green points are yet in a different region if I look at the points from this side. Which means that classification along this direction will allow me to separate at least pairs of classes well. So the goal is different. From clustering, I'm trying to find things that look similar according to a similarity criterion, typically Euclidean distance or something like that. Here I already know what is similar, because the points in the class, according to my task, is what I should identify as similar. I want all the red points should be always labeled as red. I'm trying to find a way to actually look at the data so that I see that they are similar. Imagine that I look at the data from this direction, all the three classes look exactly the same. Or if you prefer, I'm trying to find, for the binary problem, which is easier to understand, I'm trying to find a way to separate the classes by looking to a direction over which to project them. But if you look at it as a classification problem, what you're doing is I'm trying to find a separation between the classes. How? Looking for, well, in any case, that's always true. When we separate the classes with a plane, it's equivalent to say that we look for a direction over which we project the sample, and then whatever is on one side of a threshold will be labeled as class 1 and the other as class 2. And that is always equivalent to say I divide my planes with I divide my samples with a plane that is orthogonal to the direction that I chose and goes through the threshold T here. So whenever I apply this scheme, I'm dividing my classes with a linear rule, a linear plane. So you can say that LDA, if you look at it from the opposite way, is try to find a plane that separates my classes. How? Looking for the plane, which is the same as saying looking for the projection direction over which the classes look more separable. I have many possibilities. Again, I can project over this direction, which means that my separation plane will be this plane. This is not a good separation because I will make half of the points will always be labeled wrongly. I can use this direction, which means I will separate, let's say I put the threshold here, the direction itself is not sufficient. Direction plus threshold defines the rule. But let's say I put the threshold here, then these red points will be correct, these red points will be wrong, these blue points will be correct, these blue points will be wrong. Maybe something better than the horizontal one, but still bad. I can divide with this plane, which corresponds to the vertical direction. In this case, red will be correctly classified, blue will be correctly classified. Clustering, on the other hand, I have this blob of points, and I try to figure out if there are homogeneous groups. But I don't have the notion of label, so clustering will not necessarily find groups that correspond to my classes. Imagine the case where your classes look like this. So I will make an example where clustering works quite well. You have red points, other red points here, other red points here, and other red points here. They are all from the red class. Imagine this is a identity recognition problem. Person 1, person 2, person 3, and person 4. And the task is identify the gender of the person. The gender is binary, male and female. So we have two classes. Well, we simplify with two classes. Then we may have other persons from the other gender that look similar, but the persons between themselves are far. But there may be persons that look similar across the two genders. So I may have a situation like this. Let's say M and F. Clustering will do what? It will not know any label. It will group one group, two groups, three groups, four groups, because these are similar. On the other hand, what I want to do here, find a direction that allows me to put all the F points on one side and the M points on the other. This direction is a direction for LDA where the between variance, so the distance between the class means, is large, compared to the within variance, it is the spread along the class mean, because that gives me, under some assumption, we will see that it's optimal, the optimal, but it's not optimal always. In this case, it will not be optimal, but under some assumption, we show that it's optimal direction for separating the two classes. Clear? Other questions? Yes? Yes. Well, if I use LDA as a classifier, I use PCA and LDA as a classifier, but I can use PCA and LDA as dimensionality reduction before another classifier. It does, because it simplifies the model that you have to train. Now, here we're working with 1, 2 dimensions, but typical use case where we do this, and I can show you that it works in practice because it's tested. I work on speaker recognition, so identification, but with voice rather than face. It's the same, but it's... In that problem, we have lots of classes. Well, I work in what is called speaker verification. So the question is whether A and B are the same person, okay? So we have a binary problem because we don't say who is speaking, but we answer whether it's the same or not. But the training data set consists of labeled people. So person 1, person 2, person 3, person 4, and some. So what we do is we create models that, given two elements of the same or different people, are trained to answer whether these are from the same or different people. But these models are quite complex because they work on pairs of utterances, so pairs of features and so on. One way to simplify the model is to train an LDA model. Here we have a problem with many classes because the classes is the number of speakers in my dataset, so the number of identities, which typically is few thousand. So we use an LDA model to create a compact representation of this that is trained for speaker recognition, so to keep far identities, points that are from different identities, but keep close the points of the same people, and then on that we train the model that then answers the question whether two recordings are from the same. That LDA there helps because reducing the dimensionality, I throw away directions that have low information. And the problem is that the amount of parameters that I have to learn in the classifier stage is large. So if I don't reduce the dimensionality, I will start overfitting a lot. So this reduces the risk of overfitting because I reduce the dimensionality by throwing away information that is not relevant. So I simplify the classification task afterwards. If you want, and now let's just think of PCA. Imagine that you have, again, the MNIST. So imagine we apply just PCA. You have your pixels, we have said all the images here are white. But imagine that by some mistake, there are a couple of pictures that are black and they are both 0. If I train a classifier on that, it will learn that if the top left pixel is 0, then it's a 0 digit. The top left pixel is black, so it has value 0. Then the digit is 0. But then, when I test it, I have a black pixel in the top left corner, again, because it's a mistake of the scanner that scanned an artifact of the scanner. I have it for a 1. My classifier will say 0, and will say, I'm sure because the black pixel on the top is always only in the class 0. With PCA, I remove this. Why? Because if that pixel is black only in very few images, the corresponding variance will be very small, because it will be 1 for almost all images except a couple of zeros, which means that if I have to show on a graph those pixels, I will have that for a couple of images, that component will be 0, and for all the rest, it will be 1. So the mean will be very close to 1. The variance is the square distance from the average square distance from the mean, which will be dominated by these values because they are a lot. So the variance will also be close to 0, which means that PCA will say this direction is useless. And so it will remove this kind of noise. Oh, wait, this is for the training data. It simplifies the classification so that then artifacts that are present in the training data will not be used to learn anything. So here for the moment, these are the training data that we used, and we didn't use any validation data yet. In the validation of test data, I may have artifacts that are the same artifacts that are in different classes, if these are very rare, and I don't want the classifier to learn something from that, because then it will apply wrongly to the image. Remember that I will always train PCA on these images, always. That is one thing, that the validation data will not be used to train PCA. So I will train here, but here I want to avoid those use cases where this can happen. So it can simplify the classifier work because it removes things that I know are bad for the classifier. Other? Okay. What time is it? It's a bit late. Okay, now what we will start doing now is we will see our first classifier, but not today, because to get there we need to make some progress towards how we do our font classification, and in particular the first classifier that we will see, and actually most of the classifiers that we will see are probabilistic in nature. So it's useful at this point to make some short recall and introduce some things that may or may not be known on probability. So I guess that you all revised probability during the weekend. So why do we need probabilities? Essentially because the thing that we work with are things that can be easily described as random phenomena. What does it mean, random phenomena? For us, we have complex phenomena where too many factors can influence an outcome, and therefore we model this in terms of what is called random events. The randomness essentially describes the fact that we do not have full knowledge on what's going on. For example, what is the weather like tomorrow? Well, if we had a perfect model of the universe, maybe we could predict precisely what happens for all the points in the future of the universe. We don't have such a model because it's too complex. So we know that there are many phenomena that will influence the weather of tomorrow. We treat the weather as a random event, an event that may or may not happen, and the may or may not happen is not something that is related to, we will see at least in one interpretation, to tomorrow's weather, but essentially it quantifies the fact that we are not able to know with certainty what's going to happen. So the key word here is uncertainty. Why we want to model these random events? Well, the final goal is to make predictions. So when we form classification, typically the prediction is the label that we assign to a class. We see that we can give a broader extension of this task in saying that we want to take action. So typically, why we predict the weather to decide whether we want to take the umbrella or not. So our goal may not be directly make the prediction itself, but it's more take some action based on the prediction that we make. So the final goal is, should I take my umbrella or not? In any case, this distinction is, for the moment, is not particularly interesting. We will see what it entails once we try to define how we take optimal decisions when things are unknown. For the moment, let's go back and discuss what are probabilities. Probabilities are a way to describe random events. Now, for sure, you have some, when we talk about probabilities, we have at least four things we are talking about. Three, you have it in this slide, are interpretation of probabilities, and the fourth one is the mathematical concept of probability. The mathematical concept of probability is nothing else than an abstraction, like all mathematical concepts. It's just a theory based on some axioms, which has its own truth based on the axioms that you take. And the interpretation, on the other hand, are a way to say how we describe things about the real world using these mathematical concepts. Now, the problem is that the math is the math and the real world is another thing. So there is already a problem in deciding what we mean by probability when we refer to the real world rather than to the mathematical concepts. And you can see that here we have at least three different interpretations. The first one is the typical, simplest interpretation that you probably all know. It's the classical interpretation of probability. It's essentially based on the concept of symmetry in the events that can happen. Its probability is a fraction of favorable events. What does it mean? That's the typical case. I have a coin, I can flip the coin, it will give head or tail. I have two possibilities. I assume that both of them have the same probability, which means that I will assign a probability of 1/2 to both of them. When I flip, there is a probability of going to tail that is 1/2 because I have one favorable outcome out of two. If I roll a dice, what happens? The probability of getting 6 is 1 because I have 6 possible outcomes and the favorable is 1. I roll 6 out of 6 possible outcomes. This is the classical interpretation. Probability is associated to an event, and that's the number of favorable outcomes over the total number of outcomes. Now, this is a problem because how can I define then the probability for a biased coin? All this, the classical interpretation typically relies on symmetry. All the outcomes have the same probability, so I can define the probability as number of favorable outcomes divided total number of outcomes. But now I tell you that the coin is rigged to give more times tail than head. With the classical interpretation, we are not able to give at least with what we said up to now, a good definition of what is the probability that tail will come up 30%, with a probability of 30%. There is no outcome 3 tails out of 10, because we have only tossing coin, outcome are tail or head. So with the classical interpretation, these kind of probabilities already are troublesome. The second interpretation, so we will throw the classical interpretation aside. The second interpretation that extends in some way the classical interpretation is probably what you are used to in previous courses, is the frequencies interpretation, and it defines the probability as frequencies of an outcome of a repeated experiment. So when I say the probability of getting tail is 30%, it means that if I toss the coin several times, then 30%, so a fraction of 0.3 of the times, I will observe a tail. So if I toss a number of times that goes to infinite and I count the number of times I get tail, then this will happen 3 times out of 10. Frequency of an outcome under an infinite number of repeated trials. And I guess up to here you should be familiar with this concept, right? Now, where does this fail? Because the frequencies also fails. Well, it fails in at least 2 ways. One, first of all, it requires me to define an infinite number of trials which are repeated trials. So I run the same experiment an infinite number of times. But there is already a issue in the definition. If my outcome is random, it's because there are factors that I don't control that influence the outcome. So whether I get tail or head is random because there are factors like the force that I use to toss the coin and so on that I don't control perfectly. But if I use a frequencies interpretation, I said that I repeat the same experiment several times. It can be argued if I repeated exactly the same experiment and it was exactly really the same experiment, I would get always tail or always head. I will not get 30% of tails. The fact that I get 30% of tails is because I'm not really repeating exactly the same experiment. So there is already a problem in the way we define the way we measure probability. And then the problem is also that in some cases we may not even think about an experiment that I can repeat and will give different outcomes. For example, when there are elections, you have polls that give you percentage of the votes that will go to the different parties. And that is something. But based on the polls, you may end up hearing journalists that says party A has a 90% probability of winning the election, which doesn't mean it will get 90% of the votes. Maybe it's expected to take 55, party B is expected to take 35 of the votes. Since these are far enough, they say there is a 90% probability that party A will win the election. But here you can imagine that if I repeat the same election twice in a day, either A will always win, or B will always, or A will always lose. It's not like if I repeat the same election 10 days in a row, one day will win B and the other 9 days will win A. That's highly unlikely. So here when I say 90% probability A will win, how can I explain it in terms of repeated trial? It's difficult to imagine that if I repeat the same election several times in a row, the result will change. So in this case, we need to understand what we mean by saying that there is a 90% of probability that A will win the election. Now, one possible answer to these issues, and of course, this is another interpretation that, as we'll shortly see, has its own problem, is the Bayesian interpretation, where the main difference is that we don't have probability of events anymore, but the probability becomes a property of who is talking about the event. Another problem of the frequentist approach is that you may end up hearing two people saying, for me the probability that party A will win is 90%, and then another person will say the probability that the party will win is 80%. How can we make this possible if A is the outcome of a repeated event? Even if repeating the election would give 9 times out of 10 party A winning, it will still not work if I have two different values for the probability. The problem is that in the frequentist and in the classical approach, probability is associated to the event that I'm measuring. So the probability is a quantity of what I'm talking about. In the Bayesian approach, the probability is not a characteristic of the object that I'm talking about, but it's a characteristic of the person that is talking about the object. So R1 is one person, R2 is another person. They express with the probability their level of uncertainty that something will happen. According to A, the uncertainty, or according to the first person, the uncertainty on the event A will win is low. It's fairly sure that A will win. According to the second person, his own judgment on whether the outcome A, party A will win, happens is more uncertain. There is a higher chance that that event will not happen. So probability is not anymore something that is associated to the object of our analysis, but it's something that is related to the subject of the analysis. When I say the probability of a class is, of an image being a cat is 90%, that's not a property of the image, but it's the property of whoever is expressing the fact that the probability is 90%. So it measures the uncertainty, or if you prefer, the belief, which is the opposite of uncertainty, that an event will occur. Now, how this quantity is measured, that's again would open another talk, but essentially it's related to expectations of what I will observe. So the way the Bayesians define probabilities is in terms of gains that I have by accepting a bet according to my measure of how likely is a thing to happen. For example, if I tell you, let's make a bet where you give me €1 and I give you €20 if party A wins, then if you believe that probability of party A winning is 99.9%, you will accept the bet because you think you will gain. If you believe that the party A wins is 70%, you will not accept the bet because, sorry, 70% is still high. That's the opposite. I made a mistake with the numbers. If you believe it's 90% that party A wins, you will accept because there is 10% that you will lose 1 according to your belief and 90% that you will win 20. If you believe that party A is a probability of 0.01% of winning, even if the turnoff if it wins is large, you will say I'm almost sure that I will just lose €1. and there is a chance that I will win 20, but it's so low that my expected gain with this bet is lower than 0. So I will lose by accepting the bet. So essentially, probability measures my uncertainty, and it can be expressed as a willingness to accept a bet according to my odds that something will happen. Now, we will not need to exactly define this, of course, but we'll see that the way we represent probability will define the way then we apply the math definitions of probability to our problems. So the way, the interpretation that we follow will guide us to choose how to represent our objects. Now, here it's not said, but typically we'll follow a frequentist interpretation because it's typically easier to develop model under this interpretation. But the frequentist interpretation, we have seen, has several issues, so sometimes we will see that it's better to use a Bayesian interpretation, and that is the interpretation that we will use when trying to figure out how we can take optimal decision from the probabilities given by a classifier for the different classes. But we will see that much later than this week. So for the moment, we'll focus on the frequencies because it's easier, but know that there are some issues with the frequencies that we will try to hide under the carpet as much as possible, but it will not always be possible, and we will say something about that. Okay, questions? In particular, we will need to work with the subjective interpretation of probabilities whenever we start introducing multiple classifiers, whenever we start to want to understand why a classifier optimizes some objective or makes some decisions based on probabilities that may look subjective, and indeed we will see that's because they are subjective, but we will see that later. Now, the first thing that we have here is a short recall on the notions of probability that we will need. I will go quickly through this because I guess that you should have studied these things in previous courses. We have a definition of the axioms that we will use, but typically we don't need to refer to the axioms, so I will go quickly through this. Probability is defined by defining a set of possible outcomes, then events that are subsets of the set of possible outcomes. This is the collection of events defines the things that we can express probability about, and the probability is nothing else than a function that goes from events, so from the set of events to the real line, with the probability that the probability of the whole set of outcomes is 1, and then other probabilities that you have studied that define how we can build probabilities out of disjoint sets. In any case, these are the axioms that we need, but we will not really use them. Let's see with an example that's easier. We have a set of outcomes, rolling a die. We have a set of outcomes that are the numbers that we can obtain. An event is a subset of omega. So rolling 6 is an event. Rolling an even number is an event. It's a subset of omega. The probability defines a measure, a function that assigns to the different events a number. And notice that we use the word assign because, again, the focus is not on the probability being an object, a characteristic of the object, but it's whoever is talking about some event that decides which function it should use to model that object. So it's us that assign a value of probability to the events. It's not the events that possess an intrinsic metaphysical value for the probabilities. For example, if we assume that the events of the tossing die should be staying with the same probability, that's the classical interpretation, then this probability should be 1 out of 6 from the axiom that the total probability should sum up to should be 1. And the other axiom that says that if I merge all these, I will get the probability, that the total probability is the sum of these 6 probabilities. Combining the axioms, we will end up that this should be 1 out of 6. With the same assumption, we can end up that the probability of even number is 1 over 2, because we decided to assign the same probability to all the values. Another thing that we will need is the concept of conditional probability. That's the probability of the joint event A and B, so the intersection of A and B, divided the probability of B. And one thing we should pay attention, that A given B is not an event, because A is an event. A given B is the probability of A given B is actually defining a new probability function from the set of events to real line. It is the value that I assign to each of the possible outcomes when I assume B, given B. And it's defined by this expression. So it's not independent on the original probability function P, because it's defined in terms of the original probability function. But what we are doing is not defining an event, but just defining a new measure for the likelihood of the events. Here I have an example of conditional probability. We roll a die and somebody looks at it and tells us it's not 1, but doesn't tell us anything else. So what's the probability that is 2 or 3? So, sorry, what is the probability that is lower than 4, so 1, 2, or 3, given that is greater than 1? It's probability condition on B, and this, the intersection, 2 and 3, divided the probability of B. The probability of intersection is 2 over 6. The probability of this is 5 over 6. So the result is 2 over 5. Now, Bayes' formula allows us to relate the probability of A given B to the probability of B given A, which happen to follow this rule. And if both P of A and P of B are different than 0, then we can bring each other on the other side. Here, when we write something at the denominator, it holds, of course, only if the thing is different from 0. Then we have the concept of independence. Two events are independent if the probability of the joint event A and B is equal to the product of the probabilities. Here you have an example of how to derive P of B given A from the other terms. So here we had B, the number is greater than 1. A, the number is lower than 4. We had computed P of A given B. Now we want to compute a probability that is greater than 1, knowing that it's lower than 4. And you can retrieve it applying the Bayes rule. Next, the other thing that we will need, actually the only thing that we will need, are random variables. Random variables are what? Are functions defined from events to the real line, and they are defined over in such a way that for any real value x, we can compute the set of events that are, we can compute a set of outcomes for which the random variable takes a value lower or equal to x, and this is an event. So it makes sense to talk about the probability of the event obtained by assuming that the corresponding random variable is lower or equal than x. Let's make an example that's easier. We roll 2 dice. The outcomes are all the possible combinations that I can obtain about the 2 dice. A random variable of this is the function that associates to each element of omega the sum, let's call it the sum of the 2 values of the dice. It's the result of the roll. So each component has the outcome of the first die and the outcome of the second die, and the random variable given a roll, a possible outcome, gives me a real number that is the sum of the values on the dice. This is an example of random variable. For this random variable, it makes sense to ask what is the probability that the sum of the two dice is lower or equal than a given value. That is what? That's the probability of the event made up by all the outcomes for which the sum of the values, so the value of the random variable, which is a function, is lower or equal than x. For example, the probability that x is lower or equal than 4 is the probability that the sum of the two dice is lower or equal than 4. So I take all the values of the outcomes, the set of all the outcomes that corresponds to the property, the sum of the two dice is lower or equal than 4. That is the event for which I want to compute the probability. And here we count its same probability, so it's easy to count. It's 6 out of 36 possibilities, so it's 1 out of 6. So essentially, random variable, given an outcome, it gives me a number. And then I can ask, what is the set of outcomes for which the random variable is lower or equal than some value? So what is the set of outcomes for which the sum of the two dice is lower or equal than 4? And then I can compute the probability of that event. So the probability of the set of outcomes for which the sum of the two values is lower or equal than 4. Now, since we can define the probability that x is lower or equal than b, that allows also to define the probability that x is greater than a given value a, or if you prefer, the same b. So these are also events. And furthermore, we can also define the probability that x is equal to a specific value. So all these are well-defined probabilities. Then how we compute them is a different matter. We actually will not. Now, given a random variable, we have seen that it makes sense to talk about the probability that the random variable takes a value smaller or equal than small x. This, as a function of small x, is called cumulative distribution function. It gives me, for every value of small x, what is the probability that my random variable will get a value that is smaller or equal than small x. The cumulative distribution function is between 0 and 1. It's non-decreasing. If x increases, then the cumulative increases because the set of outcomes becomes larger. The limit towards minus infinity is 0, and the limit towards plus infinity is 1. At some point, all the outcomes will be considered, so the distribution will be the probability of the whole possible set of events. It's like continuous. If I compute the limit from the left the function is continuous, it may not be continuous from the right. So it's continuous when it comes from the left. Which also means that the probability that the random variable takes exactly a value will be different from 0 if and only if the random variable, the cumulative distribution function, is discontinuous from the left. Example, rolling the die. The function gives for every value of x the probability that the random variable is lower or equal than small x. If I plug it 0 here, if I plug any value lower than 1, then the probability that x is smaller or equal than a value lower than 1 is always 0, because x must be at least 1. When this becomes exactly 1, then the probability becomes 1 over 6, and I have this jump. The probability will be 1 over 6 for all values of small x between 1 and 2 excluded. When I plug 2, that's the probability the random variable is lower or equal than 2, it becomes 2 over 6. So this is the cumulative distribution function. Now we say that the random variable is discrete if the values that the random variable can take are a set of discrete values. For example, for rolling the dice, the random variable can only be 1, 2, 3, 4, 5, 6. If you have 2 dice, it can only be 2, 3, 4, 5, 6, 7, up until 12. So the cumulative function is defined over all the real line, but the values that the random variable can really take are a discrete set of values. For this discrete set of values, we can define what is called probability mass function, which is also called discrete density. That's the probability that x will take exactly that value. And it has this property, it's always greater or equal than 0. It will be 0 for all the values that that the random variable cannot take. The random values that the random variable can take are also called the support of the random variable. And it will be different from 0, well, for all the values that typically different from 0, not necessary, but it will typically be different from 0 for those values that the random variable can take. And if we sum the values of the random variable over the whole support, then the sum will be 1. Remember that for each x in the support, this will be equal to the probability that the random variable takes exactly that value. So this is a set of probabilities that must add up to 1. So the sum over all the support must be 1. From the density, we can compute the cumulative distribution. The cumulative distribution up to x is obtained by summing the value of the density over all values t that are lower or equal than x. Example, when we roll a 6-sided die, we have 1 out of 6 outcomes, and we have a probability mass function that is 1 out of 6 for all the values that the random variable can take. If we roll 2 dice, then these are the outcomes, and one probability function for these outcomes that is consistent with the probability that we have introduced before, so with the assignment that we have, would look like this. This is a probability mass function. For each value that the random variable can take is different from 0, and it's actually 0 everywhere else. So the function is defined over all the real line, but it's 0. Now we can have a discrete random variable that has an infinite number of values. So that can take an infinite number of values. For example, if you consider the problem of tossing a coin until it comes up head, the possible outcomes are I get head, tail followed by head, 2 tails followed by head, 3 tails followed by head, and so on. We have an infinite number of outcomes. You can define a probability for all of these outcomes, here you have in the slides, and you can define a random variable that essentially for every outcome gives you the number of tails that I obtained before the first head. This is a random variable because to any sequence of tosses it associates a number. Now this random variable gets an infinite number of possible values. For whatever value, that's the probability that I obtained. So x equal to whatever small x means that I obtained a sequence of small x tails before I obtain a head. So it makes sense to compute what is the probability of having x tails before obtaining a head. And that's, by the way, called geometric distribution that we will not use. Now, we have seen discrete random variables take a set of discrete or countably infinite number of values. There are random variables that can take any value over the real line or in a subset of the whole real line, but in a dense subset of the real line, not discrete. Now, in this case, we define these random variables as, well, we see that these random variables typically are continuous random variables, that is, random variables for which the cumulative distribution function is continuous. We have seen that if it's discrete, then we can define the probability mass function, that is the probability that the random variable will take a specific value. But we have seen that for this probability for a specific value to be different than 0, then the cumulative distribution must be discontinuous, because in any case, the probability that the random variable takes a 0 is the value of the cumulative in x0 minus the limit from the left of the cumulative distribution function. So for this to be different than 0 at x0, it means that the function, the cumulative, is discontinuous in x0. And for discrete random variable, the discontinuity happens exactly at the points where the random variable takes its value. If the random variable, the cumulative distribution is continuous, we say that the random variable is a continuous random variable. In this case, notice that for any point, the probability that the random variable will take exactly that point is always 0. Continuous random variable has a 0 probability of taking any specific point, but it may have a non-zero probability of taking a value inside an interval. That's because the intervals are dense, so the probability of a single point in a dense interval like the real line is 0 for any points, but that doesn't mean that, that the probability of the whole interval is 0. In this case, of course, it doesn't make any sense to say the probability mass, because the probability of any single point is 0, but we have something that behaves similarly as the probability density for discrete random variables. For continuous random variables, we introduce the probability density, that is a function that is, again, always greater or equal than 0, can be integrated over the real line, and the integral over the real line is 1. Now, any function that is a density and such that the cumulative distribution corresponds to the integral of the density function is called a density for our random variable. So if we have a random variable and we have its continuous distribution function, if we can find a density function f, which is a density and for which this equality holds, then we will say that f, the small f, is a density for the random variable x. And we use a rather than the, because the densities are non-unique. If I find one, I can define an unlimited number, an infinite number of equivalent densities. Again, this is something that we will not do, but just to say that there is, mathematically it's not the same. We don't have a single density, but it's better to talk about one density. Among all possible densities, the one that we will use is the derivative of the cumulative function. We can show that if the cumulative distribution can be differentiated, then its derivative is a density function for x, and it's the one that we will typically use. Now, densities can take greater values than 1, values that are greater than 1, because remember that they don't represent directly probabilities. A density is not a probability of a value. The probability for random variables are non-zero only for intervals, and the probability of an interval is obtained by integrating the density over the interval that I want to consider. So what is always lower or equal than 1 is this integral, not the density itself. Why? Because I don't need the density to be lower or equal than 1 everywhere for all the integrals to be actually lower or equal than 1. For example, if I have a function that is defined between 0.9 and 1 and is tall 10, then the integral of this function is always whatever I use as extremes. The integral will always be lower or equal than 1. Why? Because the integral over the real line is lower than 1. Remember that if this holds, since f is always positive, whatever the limits of the integral, this will always be lower or equal than 1, because the integral over the real line is 1, and the function is always positive. I'm measuring the area under my curve, but my curve is always above the real line, so each slice of the curve will have a positive or 0 contribution. The overall contribution is 1, so whatever subinterval I take, it will not have an area equal to 1. So this is consistent with our definition of probabilities. Okay, let's stop here. Tomorrow we will introduce the extension that we will need that are random vectors. Now, for the next part, again, last week there were quite some imbalance in the laboratory. So again, before you force me to check presence, please listen to me a moment. Try to follow the separation in squads. Why? It's not because I like that you come here Friday from 5:30 to 7. That's because laboratories up to now were fairly easy. They will become much more complex as we go through the course. If I have 60 people in one laboratory, I will not be able to answer questions at some point. So you will not get answers because I cannot follow 60 people with code that doesn't work for the upcoming laboratories. So please follow the schedule, because otherwise you will not get answers during the class. So that's going to your detriment, not mine. Okay, for those at home, again, as usual, I will close this class and open another one for the laboratory.